For the Rover Egress design group, I'm Hannah.
I'm Anton.
And I'm Zach.
Okay, so some of the things we're going to talk about are our final ramp design. We made a couple changes based off simulation results. We changed some things about the hinges and the joints, designed a deployment mechanism, ran some composite analysis in ANSYS, and finally we have some future work that we're going to talk about and fabrication methods.
So yeah, we now have a finished design. It's completely ready to manufacture. We've actually sent out our plans to a few different manufacturing companies. To do this, we have finished drawings and DXF files of all the necessary components. Here's just one example of what that looks like, and then we have a finished bill of materials there from McMaster, and just waiting on parts now. So some major modifications we made since our last presentation. A lot of it's been in the hinge design. As you may remember from our last presentation, we had a acrylic prototype model which it snapped when someone was trying to actuate it. And although that's obviously not exactly what happens with aluminum, it still gave rise to some good points that there's a lot of moments and torques in these hinges. So we basically beefed them up a little bit, made them a little stronger, as you can see here. Another thing we flushed out a lot better is the hinge deployment mechanism. As you can see here, we went with the linear spring that we talked about last time, and we also put a lot more design into the lever arm there, made it really strong. It's going to be experiencing some pretty high torques. And yeah, it should be relatively compact and effective for what we need. And last major advance is in the flange bolt design. We didn't have this for our last presentation, but now we do. As you can see here, we have it's basically just a bar, two bars that intersect here, and they're held together by a flange bolt. When that is released, it causes the ramp segments to come unconnected and allows it to deploy via the springs. Because we're going to be doing multiple tests on this, we didn't want to just rely only on flange bolts because they're relatively expensive and they only have a certain amount of uses. So we're going to be using a hitch pin, which we've ordered. That's shown there. So basically, it'll work. Just a bolt with a string or a chain attached. It'll go through right where the flange bolt would go, and you will be able to just pull it loose, and that'll actuate the entire mechanism.
All right, so some of the other changes we've made have been to the folded sheet metal ramp segment design. We've gone through a number of things. We've added a flange, increased the height using our scalable CAD framework. We didn't give it a taper. We'll talk about that a little more. We changed the pattern on the base and reduced the thickness. So the first thing is the base pattern here. We're having a lot of problems with high stresses and stress concentrations when there was a large force in the middle of that X, when basically if you have a wheel that's rolling across and the only thing it's contacting is that one point, you have a whole lot of stress in these. So we changed the pattern. We tried a few different ones, and this star pattern had some good results, so we're going to go with that. Secondly, we went a little bit back to basics. We did some force and moment calculations on the ramp segment. So this is a 96-inch ramp. So that's two segments as they're deployed. You see here the load from each rover wheel on the top. We did some hand calculations to begin with, but we realized that what we're really designing for is the maximum moment that's on any single ramp at any point. So as the rover rolls across, the moment on the ramps actually changes dramatically and traces out this red pattern that you see here that represents the maximum moment. So you use that, you get this pattern, and you can basically use this to inform your truss design. And typically, you'd use something kind of like this, where you'd have this more tapered edge and a changing cross section. And we considered that. So we went through with some different models and performed some iterations on it. And eventually, we decided that this kind of added some manufacturing complexity. There were some issues of how we get these bends in there, how we connect the two kind of non-parallel lines and so forth. So eventually, for simplicity, we ended up just using this design, and we think it's a pretty good analog for it. Also, we did some buckling studies. We did some hand calculations in FEA, and this flange over here, this area drawing over here is representing the flange that's been put on the top of these vertical members to reduce the chance of buckling and to basically give it some more resilience to the axial force it feels. So we found a factor of safety of 3 for that, so we're in a good ballpark. Lastly, we performed some optimization using that scalable CAD model we had. We changed the dimension, and we performed an FEA and saw what the maximum stress was. So these are all scaled from 0 to 1 for clarity. For example, if we change the sheet metal thickness, you can see the strength to weight ratio and the factor of safety increases monotonically. For some dimensions, like the fillet radius, it kind of goes up sharply and then plateaus. So we can pick a number around here that's fairly optimal. For some of them, there's a trade-off between strength to weight and factor of safety. So that's interesting. And some of them didn't really show any good relationship that we could use to optimize. So we chose those dimensions based on different reasons. So yeah, that's the basic summary of what we've changed for the ramp segment.
Once we had our final design, we did run some simulations in ANSYS to ensure that we still had an appropriate factor of safety. So that's the results. And we also wanted to ensure that this design, even though it's going to be used on Earth, could have a changed material, and the test would also be useful for a lunar environment. So the aluminum design is about 4 times past what the maximum weight of the ramp can be. We're aiming for 10 to 15 kilograms, but obviously you can't do that with aluminum. You'd want to do that with composite, which has a high strength to weight ratio. So we ran simulations on our final design in ANSYS using composites. And that's a little tricky, so we started with just a ramp segment with no cutouts. And we found it to be 2.25, so obviously we'll still need to reduce that. This is a preliminary composite testing result in ANSYS. And it has a factor of safety of 1.89, so it's still satisfactory, and it has a higher reduced weight. So that'll be something we do some more additional testing on before the end of the semester.